So today we have section 4.9, which is a bit of anti-calculus. We have anti-derivatives. So we spent all of chapter 3 collecting derivative rules and taking derivatives of any function we came across, and we built up a little library of differentiation rules for common functions, and we collected those all on reference page 5 of the book. But sometimes we want to do things a little bit backwards, and this is especially true in developing physics. Frequently we have knowledge about the rate of change of something, or a function based upon several rates of change if I have a more complicated differential equation that I need to solve, and I need to find information about the original function. For example, the acceleration due to gravity here on Earth is approximately negative 9.8 meters per second, with up being up and down being down. So I have a function, which is a constant function. Acceleration at time t is negative 9.8 meters per second squared. Per second, yes. So how do I calculate the velocity at a particular time? Well, since acceleration is the rate of change of velocity, I'm searching for a function whose derivative is equal to negative 9.8. And it turns out such a function is negative 9.8t. But that's not the only function which has a derivative of negative 9.8, because I could add any other number here, say 17. If velocity is equal to negative 9.8 t plus 17, then its derivative is also equal to negative 9.8 for all t. So we don't necessarily know what this number is going to be if I'm looking for the regular antiderivative of the acceleration. So in general, what we'll do is we'll try to set some kind of initial condition to try to determine what this mystery value is, and frequently we'll have information about, say, initial velocity. So let's say that this is a situation where a ball is released from a certain height. Then based on the language of this setup here, my ball is just released, so my initial velocity should be equal to 0. Over here I have 0 plus whatever mystery number, and since this needs to be equal to 0, this will also be equal to 0. So given only an acceleration, I was able to find a function describing my velocity at time t, which was a simple negative 9.8t. But I can go further. I could ask, well, how do I describe the position at time t? I'm certainly going to need to be able to use the initial height here of 10 meters, and the velocity is involved. I could say, oh, distance is equal to velocity times time, but my velocity is a variable. I have variable velocity. So I do know that velocity is the rate of change of position. So now I'm looking for a function whose derivative is equal to negative 9.8 times t. And this could be a little harder to find, but I've found that s of t equal to negative 4.9 times t squared has that appropriate value. Because if I take the derivative of this function I've declared here, I have s prime of t is equal to negative 4.9 times 2 times t. Just from using the power rule, which gives me my negative 9.8t. But again, I don't know if this is the specific value, because adding or subtracting a constant doesn't do anything after I take a derivative, because the derivative of a constant is just 0. But I do know that the initial height of my ball was equal to 10 meters. So I have negative 4.9 times 0 squared plus my mystery number is supposed to be equal to 10, which means my mystery number is actually just 10. So to summarize, given just an acceleration, negative 9.8, an initial velocity of 0, and an initial height of 10, I was able to find, I guess, source functions explaining the behavior of my ball. V of t is equal to negative 9.8 t, and s of t was equal to negative 4.9 t squared plus 10. And in fact, in terms of physics, I can generalize this. Given a constant acceleration, my velocity is always equal to acceleration times time plus initial velocity, and my position is always equal to acceleration divided by 2 times t squared plus v0t plus initial position. In this process of hunting for things which have the right derivatives is looking for antiderivatives. And we usually declare them with capital letters. So we'll say an antiderivative of a function f of x is some function big F of x such that f prime of x, big F prime of x is equal to little f of x. So my big F is an antiderivative if the derivative is what I have on hand. If g of x, I'll say it this way, g of x equal to big F of x plus 12, for example, is also an antiderivative of f of x, since g prime of x is equal to big F prime of x plus 0, which is equal to little f of x. So given a function f of x, the most general antiderivative is going to be any particular antiderivative you may have already found plus a constant, c. We just label it plus c. It's a nice letter. So in the cases of my physics example up above, my plus c turned out to be equal to my initial velocity and my initial height. But there are other ways to find those. So the big question is, how do we find antiderivatives? And the short answer is we don't. We just kind of have them. Every time we have a differentiation rule, we read it backwards to get an anti-differentiation rule. So for example, if I have f prime, then I have an associated anti-differentiation rule, f to big F. For example, if I had x to the n, that derivative is n times x to the n minus 1. If I try to undo that, how did I do the power rule? I took the exponent down, and then I decreased the exponent. And I should do the opposite things in the opposite order. So let's try this. If I have x to the n, I should increase the exponent, and then divide by the exponent. And you can check. If I take this big F over here and try to take its derivative with respect to x, I'm going to bring down the n plus 1 to cancel with the n plus 1, and I'll reduce the exponent by 1, bringing it from n plus 1 down to n. If I had e to the x, this one's fun, then the derivative is e to the x. So if I have e to the x, then the antiderivative is e to the x. If I have sine of x, that derivative was cosine of x. So if I start with cosine of x, my antiderivative is sine of x. Always be careful of which direction you're trying to go for these calculus problems. Don't mix up your derivatives and antiderivatives, especially with the sines and cosines. If I start with cosine, my derivative is negative sine, versus the antiderivative of cosine is a positive sine. If I start with a sine, then the antiderivative will be a negative cosine. If I start with a tangent, my derivative is secant squared of x. But if I start with a secant, I don't know any functions whose derivative is equal to secant of x. So in those cases, I'm stuck. But if I do start with secant squared of x, then I'm going to have an antiderivative of tangent of x. And similarly, I don't know any functions whose derivative is equal to tangent of x, so if I'm trying to find an antiderivative of tangent of x, I am likewise stuck. So be sure to know reference page 5 forwards and backwards, especially by the end of calculus, because you're already supposed to be able to take the derivative of everything, but the antiderivatives are going to be necessary in the coming chapter. I said etc. here, but I have a couple of special mentions. Natural log of x has a derivative of 1 over x, but natural log of x only exists on one side of the number line. I can't take the natural log of a negative number, for example, but 1 over x exists for negative numbers. So specifically, the derivative of this other function, the natural log of the absolute value of x, this will also be equal to 1 over x. And I can check that simply by doing the two cases of the derivatives, if I have a positive x value or a negative x value, since x is never equal to 0. So if f of x is equal to 1 over x, then the antiderivative, big F of x, will be equal to the natural log of the absolute value of x. And similarly to what I did for the product rule, since the derivative of a to the power of x, what did we do for these? We rewrote it and then multiply by the natural log of a. So you can guess what happens in the antiderivative. Instead of multiplying, I'll divide. So if f of x is equal to a to the x, then big F of x is equal to a to the x divided by natural log of a. But we can't do much more than this because we don't have any rules for antiderivatives. The best I can do is distribute across addition and subtraction. So if I have f of x plus g of x, then this follows the same rules as the basic differentiation rules. I'm going to have big F of x plus big G of x. And if I have a constant multiple, then I'm going to get a constant multiple. But I can't go any further than that. For antiderivatives, I have no product rule, I have no quotient rule, I have no chain rule. Is there another rule? I don't think so. So if I have too complicated of a function, then I'm going to need to try to either simplify it or probably just give up. So if I was given something like, suppose we know that h prime of x is equal to cosine of x plus x squared minus x over the square root of x. We need to know h of x. So I'd be looking for an antiderivative to this stuff over here. And the cosine, that's fine. I have that in my chart. I know that the derivative of sine is cosine. So I can start off by saying h of x is equal to sine of x plus. But then how do I handle this fraction over here? I don't have very many options. I have a backwards version of the power rule, but I don't have any quotient rules or anything like that. So what I should do is I should rewrite it in simplest terms possible. I want the most basic functions I can possibly come up with. So cosine of x, I can't go much past that. But x squared minus x over the square root of x, I can rewrite that into separate fractions. And I can rewrite the square roots as powers. So this is x squared divided by x to the 1/2 minus x to the 1 divided by x to the 1/2. And when I divide, I subtract the exponents. So this is cosine of x plus, that's 2 minus 1/2, so that's x to the 3/2 minus 1 minus 1/2 is x to the 1/2. So now if I want my antiderivative, I'll say the derivative of sine is equal to cosine, so the antiderivative of cosine is sine. And then the anti-power rule, I'll call it, I have to increase the exponent by 1 and then divide. And I have to, no, not plus. And I have to increase the exponent by 1, 3 over 2, divided by 3 over 2. But I still wouldn't be done because there's always a plus c when I take an antiderivative. For this problem, I didn't give any information as to what the plus c could have been, so I won't be able to find out what it will be. I'm not going to spend the time to write out every single antiderivative we can possibly take, because really what we just need to do is look at that reference page 5. We look at all of our differentiation rules and try to know them backwards now. These antiderivatives are about to become very important because, as we're going to learn in section 5.3, the antiderivative is actually the same thing as attempting to find the integral of a function. And the integral does technically a lot more than just finding antiderivatives of functions.